Hey guys, Mr. Backward here. In this video, we're going to take a look at the definition of a derivative. So as far as what the derivative actually is, the derivative of a function f with respect to the variable x is the function f prime, that f with a little apostrophe on it, we read f prime, whose value at x is the limit as h approaches 0 of f of x plus h minus f of x all over h, as long as this limit exists. Now, this is something that we've actually seen before. If we remember doing slopes of tangent lines, this derivative is exactly the same thing. It's the same exact process. Then, if f prime exists, we say that f has a derivative, or that it's differentiable at that x value. A function that is differentiable at every single point along its domain is called a differentiable function. So in this example, we're going to differentiate or find the derivative of the function f of x equals x squared. So we're going to be looking at the limit as h approaches 0 of f of x plus h minus f of x all over h. So the first thing we're going to take care of is that f of x plus h. So that means in our x squared function, where we see the x, we're going to replace it with x plus h. So this becomes x plus h squared. Then we do minus f of x, and that's just the original function. That's just the x squared, and this is all over h. Now, we want to work on simplifying this down. So what we're going to do is start with that x plus h squared. Squaring that really means we're multiplying it by another copy of x plus h. So we're going to have to FOIL that out. X times x is x squared. X times h gives me xh. H times x gives me another xh. And then h times h gives me h squared. But then I still have this minus x squared on the back end. And this is all over h. Now I'm looking for like terms that I can combine and maybe some things to cancel out. So what I notice is that I have this x squared in the front and a minus x squared on the back end. Those are going to cancel each other out. I have an xh, and then we're adding another xh. So I can combine those to get 2xh plus h squared all over h. On top, I notice that everything in that has h. So what we're going to do is factor h out of the numerator. So that's going to leave me with 2x plus h all over h. Then we're going to be able to cancel out these h's that are in the front, and that leaves us with 2x plus h. Now we're not done because we haven't done this limit yet. So we still need to take the limit of this 2x plus h as h is approaching 0. But now that we went through and did all of that algebra and canceling, it's safe for us to direct substitute the 0 in there for the h. So we would get 2x plus 0, which is just 2x. So the derivative of this f of x function is just 2x. Now, if we want to find the derivative at a specific point on our function, we can adjust that limit just a little bit. So if we want to find the derivative of f at the x value of a, what we're going to do is take the limit of f of x minus f of a all over x minus a, and we're going to do that limit as x is approaching a. And we can do that as long as this limit exists. So in this example, we're going to use that alternate definition to help us differentiate f of x equals the square root of x at the x value of a. So again, we're doing the limit of f of x minus f of a all over x minus a, and we're taking this limit as x approaches a. So as far as that f of x at the very beginning, that's just the original function, the square root of x. And then we have to do minus, now we're going to do f of a, so that means plug a into that function. So this is going to be the square root of a, and then this is all over x minus a. Now, in order to get things to clean up in here, we have to do a little rationalizing with the numerator. So I see the square root of x minus the square root of a. So what we're going to do to rationalize this is multiply by the conjugate. So what that says we're going to do is, since we have the square root of x minus the square root of a, the conjugate is the square root of x plus the square root of a. So we just change that sign in the middle. And we're going to multiply by that on top and on bottom. On top, we're going to work on foiling this out. So the square root of x times the square root of x gives you just regular x. If I take the square root of x times the square root of a, I can't really put those together, so I'm just going to leave it as plus root a root x. And then if we take this negative root a times this root x, we're going to get minus root a root x. And then if I take negative root a times positive root a, I'm going to get minus a on top. And then on bottom, we have x minus a times the square root of x plus the square root of a. Notice I didn't do the foiling on bottom because there's going to be some canceling that happens in here. If I start on top, though, I see plus root a root x and minus root a root x. Those are going to cancel each other out. So on top, we're left with x minus a over x minus a times that square root of x plus the square root of a. And what I see happening is that we have x minus a on top and on bottom. So those are going to cancel each other out, leaving me with just 1 over the square root of x plus the square root of a. But I still need to do this limit. I have to take the limit of this 1 over root x plus root a, and we're going to do that as x approaches a. So in here, I'm going to direct substitute the a in for the x. So I get 1 over root a plus root a. And if I take root a plus root a on bottom, I get 1 over 2 root a. And now what I could do, if I knew a specific a value that I wanted to do this derivative at, I could just plug that number in for a here, and it would tell me what the derivative is at that specific value. Now, last thing we're going to focus on is just a little notational stuff as we're looking at derivatives, so different ways that derivatives can be written. We've already seen f with a little apostrophe on it, which means the derivative of f, or we could read that as f prime. We could also write it as y with a little apostrophe on it, which we would read y prime. And there's advantages and disadvantages to these different notational things. This one is pretty brief, but it doesn't really name what your independent variable is. Versus, if we compare that to our next one, this is dy dx, or dy over dx, or you could say the derivative of y with respect to x. Now that names both of your variables. It names your y variable and your x variable, and it also uses d to represent the derivative. This one is very similar. This is df over dx, or we could just read it df dx, or the derivative of f with respect to x. And this one is nice because it emphasizes the name of the function, so using that f in there. And again, we're using d to represent the derivative. Another way that this could be written is d dx of f of x, or we could say the derivative of f at x. And the nice thing about this one is that it really emphasizes the idea that differentiation, or finding a derivative, is actually an operation that you're doing to a function. That's going to be it for this video. Thanks for watching.